I'm Professor Rad, and this is Precalc Video 3.1, Trigonometry Definitions. In this video, we'll be taking some basic trig definitions and generalizing them so that we can now graph trig relationships on a Cartesian plane. So that's going to be our goal in this video. And we will be talking about both degrees and radians and a little bit of the pros and cons of those two and why sometimes it makes sense to use degrees and other times it makes sense to use radians. So to start out with, I am going to operate on the assumption that you have seen these definitions before. So you may remember the saying SOHCAHTOA. So that's sine is opposite over hypotenuse. So that's SOH. CAH, cosine is adjacent over hypotenuse. And TOA is tangent is the opposite over the adjacent. So if we look at what's going on with this triangle, we have a right triangle. And if I have the angle theta, the opposite side is the side that's opposite theta. The adjacent side is the leg that forms the angle along with the hypotenuse, which is opposite the right angle. So this is a good way to remember these. SOHCAHTOA, I learned it as Tom's old aunt sat on her coffin and howled. Right, so Tom's old aunt sat on her coffin and howled. Very appropriate for the Halloween season, which is soon upon us. So you can remember it whichever way is going to make most sense to you. So the first thing that we're going to do is we're going to think of this triangle as if it lives on a Cartesian plane. So I'm going to redraw this same diagram, but I'm just going to draw it on an XY axis. So here's my triangle. So this triangle here is this one here. And what I'm going to do, oh, here's my angle theta. And what I'm going to do is I'm going to plot this point here where those two sides meet. So the reason I'm doing that is because this point has an x coordinate that matches this adjacent side. And this point has a y coordinate, so y value, that matches the opposite side. So if I have a point x, y, I can now think of the adjacent side as x, and I can think of the opposite side as y. So this is going to give us a way to find a relationship between this triangle that we're finding our trig values for and the Cartesian plane. Now also, I'm going to need a value for this side here, and I'm going to call that r. And I'll explain why we picked r a little bit later. It'll become evident why r is often used in this case. So we can rewrite these relationships as sine of theta is going to be the opposite over the hypotenuse. So it's going to be y over r. Cosine of theta is going to be the adjacent over the hypotenuse. So it's going to be x over r. And then tangent of theta is going to be the opposite over the adjacent. So it's going to be y over x. And lastly, just to make sure everything kind of has a nice, neat relationship to each other, because this is, ooh, I didn't mean to doodle there. Because this is a right triangle, that means we can apply Pythagorean Theorem to express a relationship between the two legs and the hypotenuse. So we know that x squared plus y squared is going to equal r squared. So there we go. That's how we can translate this free-floating triangle into something that's now graphed on the Cartesian plane. Now, what this allows us to do is it enables us to broaden our definition of these trig relationships to outside of living in a triangle. So for example, in this picture that I drew the angle, I'm assuming it's coming up from the x-axis and going towards, excuse me, that diagonal line. But there's nothing that says I have to live in the first quadrant if I'm on a Cartesian plane. So for instance, I could be living over here in quadrant 2. So I could have a point xy over here, where now x is a negative value and y is positive. Couldn't have that with a triangle. right? With a triangle, distances are always positive. But when I'm on the Cartesian plane, now I can have some values that are positive, some that are negative. And I can have an angle that's bigger than 90 degrees, which again, we can't have if we're living in a triangle, because in a triangle, the sum of the angles has to be 180, and we have 90 for a 90-degree angle. So we can use these definitions for our Cartesian plane to expand our concept of these relationships to outside of just triangles. And r is still going to be the distance of this side. Now, when we're forming these definitions, we can also form three other relationships that are the reciprocals of the three we've written here. So those relationships are going to be called the cosecant, the secant, and the cotangent. So cosecant, which we're going to write CSC, because we want to stick to three letters for trig functions. CSC of theta is going to be r over y. Secant, which is SEC of theta, that's going to be r over x. And cotangent, which is going to be COT of theta, that's going to be x over y. So we've now broadened our definition of trig functions beyond just living on a triangle. We've broadened them to the Cartesian plane, so we can define them for any ordered pair xy, and these are the ratios that we'll be using. So if you are taking Precalc with me, I will have passed out in class if we're on campus, or I will post it to Blackboard if we're online, a trigonometry fact sheet. So whenever we do a definition or state some identities, we want to make sure that we're summarizing them on this packet here. This packet, I've had students who took Precalc with me in future semesters email me asking for this packet because they've lost theirs, or they've emailed me and told me that they're using theirs in calculus and it's such a great reference to have. So my recommendation is that make sure you have this and you fill it out as you walk, as we go through these videos. So we've just filled out our definitions right here. So we have our diagram of our ordered pair, and then we've got our 6 trig functions. And then we also have this relationship that x squared plus y squared is r squared. All right, so let's do an example of applying these definitions just to become accustomed to using them on a problem. Alrighty, so I've summarized our trig definitions over here on the side, and I've made sure to write down this relationship from the Pythagorean theorem, x squared plus y squared is r squared. And here's the example that we're going to be looking at. So we're going to find the 6 trig values for the angle that's been drawn. Now, when we draw an angle in standard form, the positive direction is always going to be counterclockwise. So if I was moving in a, say, positive 60 degrees, then a positive 60 degrees would be moving up this way. So this angle theta here, the way that I've drawn it going in a clockwise direction means that the measurement of this angle is going to be a negative. So for example, it could be like a negative 50 degrees, something like that. So we're going to get into finding the value of theta in a little bit later. But just know that when you start your measurement of your angle, it's always from the positive x-axis, and a positive angle is going counterclockwise, and a negative angle is going clockwise. Now, in order to find the 6 trig values, we need to know the values for x, y, and r, since that's what we have in our formulas. So when I look at this point, let's find the x and the y value. So for the x value, looks like we have 10. And for the y value, looks like we have negative 24. So we get the x and y values from the coordinates of the point. And then to find the r value, we're going to use the Pythagorean theorem. So you do want to be careful when you're substituting into the Pythagorean theorem when you have negatives, because remember, when you square a negative, you get a positive. So I'm going to write out x squared plus y squared is r squared. So x is 10, y is a negative 24, and r is r. All right, I know 10 squared is 100. don't know offhand what 24 squared is, so let's work through that. 24 squared is 576. So we're going to get that r squared is 676. And to solve, we're going to find the square root of both sides. So the square root of 676 is going to be plus or minus 26. Now, we have to figure out whether we want the plus or the minus of this value. So when you have your xy coordinates, they could be either positive or negative. So if we were solving for either x or y, I would have to bear in mind the quadrant that we're located in to determine whether my value is positive or negative. For the value of r is representing the length of this line here. So r, because it's representing a length, is always positive. So we're going to get a positive 26 here for our value for r. So this means we've got an x value of 10, a y value of negative 24, and an r value of a positive 26. Now that we have those three values, we can determine each of these trig functions. So take a moment and find each of these values and express them as fractions in simplest form. All right, so I've gone ahead and I found each of these 6 trig ratios. So for sine of theta, I got a negative 12/13. For cosine, I got 5/13. And for tangent, I got a negative 12/5. So one of the things I'm noticing right away, now that I'm on a Cartesian plane and not just locked into a triangle, is that it's possible not only to have negative angles, but it's also possible to have negative ratios. So it's possible for sine of a value of an angle to be a negative. And that's not happening just because we had a negative angle. It's happening because we landed in the 4th quadrant. So even if I had measured and the angle going in the positive direction, maybe I would call that angle phi, then I would be getting these exact same ratios. So this is a new kind of relationship that we're getting with our trig functions. And then similarly for cosecant, I got a negative 13/12. For secant, I got 13/5. And for cotangent, I got a negative 5/12. So in each of these instances, notice that I kept my answers in fraction form. You want to keep your trig values as ratios because they are ratios of the sides of a triangle, or in this case, this diagonal here in the xy coordinates of the point. So you do want to keep them as improper fractions. You don't really want to work with mixed numbers too much, and decimals only if we're asked for a decimal value. All right, so next we're gonna do a little experiment. All right, so for this little, it's not really an experiment, but for this little journey that we're gonna take, you don't have to write all of this down. We're just gonna talk about why certain things exist in a certain way. So when we have a triangle, we know that the sum of the 3 angles in a triangle need to add up to 180 degrees. So you'll often hear there are 180 degrees in a triangle, right? And if we have a circle, so if we were to, I don't know, pick our radius here and walk all the way around a circle, we would have walked 360 degrees. So there's 360 degrees in a circle. Why? Why do we have 360 degrees in a circle instead of like 100 degrees? Right, so if we think about like the metric system is based on measurements of like powers of 10, because those are easy for us to compute with because we operate in base 10. That's the number system that we have developed and use now. So the reason there are 360 degrees in a circle instead of say like 100 is because the ancient Babylonians are where we get our degrees from, and they worked in base 60. So that's where 360 came from, because they worked with a base 60 system. It's also incidentally why we have 60 seconds in a minute and 60 minutes in an hour. So those divisions of 60 come from the ancient Babylonians, instead of having like 100 seconds to a minute and 100 minutes to an hour, right? So that would make arithmetic a lot easier and those conversions a lot easier than dealing with the 360. So this 360 degrees is an arbitrary amount that we've just sort of inherited from eons of using them. So what we want to do, if we're going to be defining functions on a Cartesian plane, is we could use 360 degrees, but that would mean if I were to have an angle of just 1 degree, right, that would have to be 1/360th of the circle, which is kind of weird. It's kind of weird to think in terms of 360ths, especially because it's an arbitrary number. It's just, we could have picked anything literally. So instead, what we're going to do is we're going to adopt a measurement of angles that makes more sense when we are moving our angle on the Cartesian plane. So what I've done here, I've drawn a circle, sort of, we're going to pretend it's a nice circle, and it goes to the point R0. So what that's telling us is that the radius of the circle is R. So remember, if you have a circle on a Cartesian plane that is centered at the origin, the formula for that circle is x squared plus y squared equals r squared, right? A nice connection. So we want to have these nice connections as we work with our trig functions. So if I think about an angle that's going through a point xy, right, so here's my angle that's being drawn. Also, I apologize if you hear the hum of my computer. It's been working all day and it's very warm right now, so it's just going to start making a humming noise. You might have heard it all along, I don't know. But at any rate, so we're carving out this angle theta when we move this line. And this line has a length of r because that's the radius of our circle, and it's passing through our point xy. So far, what we've drawn here is corresponding perfectly to our trig values. So instead of thinking about, okay, what is the what fraction of 360 have we just carved out? We're instead going to relate this angle to the arc length of the circle that it passes through. So instead of thinking of an angle in terms of measures of fractions of 360, we're going to say, okay, what is the length of the arc that I carve out when I move that angle, when I move that amount? So if I think about the arc length of a circle, well, let's think about the arc length of a whole circle. So that would be the circumference. So the circumference of a circle is going to be 2 pi r. So if this arc goes, I don't know, what would we say here? Maybe a third of the way through the circle, right? So this arc length would be the amount of the circle I've gone, for example, in this case, a third of that circumference. So we would get 2 pi over 3 times r. So this is where the origin of radians comes from. So if you've heard of radian measurements refer to the arc length that you're passing through as you carve your angle, instead of referring to this arbitrary 360 degrees. Okay, so it has a connection to the motion of the angle on your coordinate plane. In order to make this easy for us to kind of think about, we're going to have r equal to 1. So we're going to think of this as a unit circle. So it has a radius of 1. And so if our circle has a radius of 1, then 2 pi r is just 2 pi. And so we would get 2 pi thirds radians. So this measure, this angle, would be 2 pi thirds radians. Since it's a third of our circle, that's going to be a third of this. So that would be what, 120 degrees. So we want to be able to think in terms of radians and degrees kind of interchangeably. In this class, we're going to be focusing primarily on radians. So we'll see degrees every now and again, but you want to make sure that you become comfortable with radians, because that's it's got this nice connection to the movement on the coordinate plane, and it's going to make things a lot smoother when we go to graph them, make it a lot nicer. I know it's weird because it's new. Everything's weird when it's new, but as we practice with it and become more comfortable thinking of it in terms of arc length, then it will become much easier, I promise. So what I'm going to do is I'm going to rewrite these definitions now in terms of the unit circle and the values there. So I've drawn my unit circle here, and I've set us up to write out our coordinates here. Now, because we're on the unit circle, I'm indicating that by this 0.10, that's indicating that our radius of our circle is 1. But you could also write out the equation, x squared plus y squared equals 1. And if we're using our formula sheet, now we're going to be filling in this piece up here. So when we have these relationships, we can just go ahead and fill that in here. So sine of theta is still going to be y over r, but r is 1. So y over 1 is just going to be y. Similarly, cosine is going to be x over r, but r is 1. So we have x over 1, which is just x. And tangent is going to be y over x, and that doesn't change. So we get y over x. For cosecant, we're going to get 1 over y. For secant, we're going to get 1 over x. And for cotangent, we keep x over y. So if I'm living on the unit circle, then these are going to be my definitions for my trig functions. So let's do an example of applying these definitions, these unit circle definitions, to a problem. Just pulling my example up here. So let's, for this example, let us determine, let's do sine of pi halves radians, cosine of pi halves radians, and tangent of pi halves radians. So we'll find these three. Now, we are going to go through the unit circle in much greater detail in a video to come. So right now, we're just kind of dipping our toe in the water, becoming accustomed to this. So when I think about my circle, the whole circle is going to be 2 pi radians, right? Because that is the circumference of the circle. That's the whole arc length. If I cut that in half to get pi, now that's going to be half a circle. So 2 pi radians is all the way around. Pi radians is halfway around. And if I cut the half circle in half, then I'm going to get a quarter circle. So this is where our pi halves radians are going to land us. So pi halves is going to be a quarter of the circle. In other words, 90 degrees. That's what we're looking at here. So because I'm on a unit circle, I know that the coordinates of this point are going to be an x value of 0 and a y value of 1, because my radius is 1. So now I can go ahead and apply these definitions. Sorry, I didn't mean to bump you here. So the sine value is the same as y. So the y value of this point is 1. So sine of pi halves is 1. Cosine is going to be the x value. So the x value of this point is 0. And tangent is going to be y over x. So tangent is going to be 1 over 0. Oh, that's undefined. So we're now going to get some weird stuff happening with our trig values. So in the last example where we applied these definitions, oops, these ones here, directly, we found that we could get negative angles and we could get negative trig values. Now we're learning we can get 2 other types of answers. We can get answers of 0. If we think about on a triangle, that would mean one of the sides had a length of 0, which wouldn't make sense, right? And we can get trig values that are undefined. So we can get some weird stuff happening using these definitions, because now we're no longer just, constrained to thinking of a triangle, we're thinking of the whole Cartesian plane. So yeah, I think ending on some weirdness is a good place to end. So we're going to stop this video here. In our next video, we're going to start to play with our trig definitions and see if we can establish some shortcuts or some relationships between the trig values. So looking forward to seeing you there for some basic trig identities. In the meantime, I hope you have a wonderful day, and I hope this helped with the origins of some of the, why we're using radians and the origins of some of these definitions. So yeah, so have a great day, and I'll see you next time. Bye for now.